Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In this video, we're going to learn some very useful and interesting concepts and tools that can help us compare different clusterings outcomes. You may not really know what do I mean by comparing different clustering outcomes to begin with. This is something that I will be covering in this video as well. So let's just look at the slides. Alright, so during the course of this video, after some very quick recap about clustering, we are going to learn about the mathematical notations of clusterings, and that is going to help us to understand how we could have metrics that are meant to compare clusterings for us. And also there are going to be two types of metrics, counting pairs and set matching, and we're going to see what are the differences and what are some of the famous metrics for each of these two types of ways that you can go about compare your clusterings. And in the end, I will wrap up the video with a summary. Before we start progressing through this video, I would like to bring your attention to a very specific way I'm going to use the language clustering. Of course, we do know when we apply a clustering algorithm on a data set, we will have a few clusters. But the whole output of a clustering algorithm is going to be known as clustering in this video. By clustering in this video, I mean clustering outcome, which basically is what each data object is a member of, what cluster each data object is a member of. And here in this video, basically we're going to learn how we would go about comparing these clustering outcomes. Alright, so we did talk about what's clustering algorithm. A clustering algorithm is when we want to find the inherent similarity and dissimilarity among the data objects using their attributes. And we use an algorithm to do that for us most of the time, at least when we have data objects that have more than 2 dimensions. All of the clustering algorithms I actually go about this grouping of the data object by making sure that the members of the same cluster are very similar and the data objects that are not the member of the same cluster are different from one another. So now let's start learning some notations that are going to be helpful for us as we progress through this video. So we call a clustering C. Remember, a clustering, what I mean by clustering is the clustering outcome of an algorithm, right? We say a clustering C is a portion of a set of the data objects or points or data set into mutually disjoint clusters, C1, right? So I have clustering C that has C1, C2, till CK. So I've got K clusters. And, these clusters are such that if you have the intersection between each of these clusters from C1 to CK clusters, the intersection of them are going to be 0, which means that there is no data objects that is a member of more than one cluster. And the union of all of the cluster is going to be equal to the D, which is the whole data objects. I mean, all of the data objects that you have. And the number of data objects that you have, data points you have, is N, and the number of data objects in each cluster, let's say CK, the cluster CK, is NK. So this is the notation we're going to be using. And of course, the summation of all of the N1, N2, N3, all the way to NK is going to be N. So, of course, we assume that there is no empty cluster, so that means that NK is always greater than 0, and means that there is no empty cluster. So, here we are going to also be using another clustering. Pay attention, we're going to compare a clustering outcome to another clustering outcome. So we've got C with all of the notations that we talked about. Now we are also going to have C prime with very similar notations. I mean, C prime has C prime 1, C prime 2 to C prime K clusters. The same thing, the intersections of each cluster. This intersection of two clusters, each two clusters are going to be empty, and the union of all of the clusters are going to be the same as the whole number of data objects. And the same with n prime k, and all of that. So this is actually n prime here, so let me correct that here. And the same thing with the number of clusters. And we also have that, there is no non-empty, there is no empty cluster. All of the clusters are non-empty. We know that k and k prime could be equal or not equal to one another. So here we have k is equal. It could be equal or not equal. It's not mandatory for us for one cluster. Let's say for one cluster to have two clusters. It could be that the other clustering that we're trying to compare this clustering to with may have three clusters. So there is no obligations that we have the same case. So let's practice these notation on this example dataset. So here we've got 20 data objects that have been clustered into three clusters. We've got orange as C1, blue as C2, and green as C3. Right, so here we've got 20 data objects and we've got three clusters. Right, so those are our notation. And we have N1 is how many? We've got 6. For N2, we've got 7, actually 6, and for N3, we've got 8, right? So you can actually count them. So these are how we, seeing these notations in this example. And of course, we can see there is no, commonality between either of these clusters. So all of them are empty sets if you have the intersection between them. And of course, this tells us about CK and CL for every possible two clusters. This holds true. And also we know the union of all of these clusters or all of the data. If there is every data object has a cluster. So we do see that the n is equal the summation of all of the cluster's members. And the same thing is true about C prime. So this is the same data set or the same group of data objects, but another clustering. Pay attention here, while k was 3, k here is 2, and n prime 1 is 10, and n prime 2 is 2, right? And everything else also holds true for this clustering. So what we are trying to learn how to go about in this video is going to be able to come up with a metric, or at least learn about the metrics that are out there that can help us come to a number that represent the similarity between these two clustering. When we perform clustering analysis, one of the things that we need to be able to do is to see if our clusterings are consistent. Remember when we were doing k-means? K-means is a random algorithm. If the clustering algorithm does not come to very similar clusterings, we may have to question if there are meaningful patterns among the data objects, because the k-means are reaching very different outcomes, right? So we need to have a way to compare clusterings so we can see if we are arriving to a meaningful clustering. And that's the goal here. We want to be able to basically capture the similarity between clusterings. So we've got one clustering on the left, and we've got one cluster on the right. We want to see how we can go about capturing the similarity between these two clusters. So there are two types of metrics that we're going to learn in this video. The first one is based on counting pairs. basically we study the state of each pair, whether they are in the same cluster or not in the same cluster under each clustering, and based on that we come up with some metrics that can be useful to compare clusterings. And then we're also going to be looking at another category of metrics for comparing clusterings, which is set matching, that is based on set cardinality, which we'll understand when we see an example of that. So let's start with counting pairs. In counting pairs, each pair is going to be studied, right? So if we go back to this data, we will have, we will study each possible pair. So first we study pair 1 and 2, and then we move to study pair 1 and 3, right? So we study all of these pairs, and based on what we see after we study all of these pairs, then we come to a metric, or we come to a number that can capture the similarity between the clusterings. Each pair may fall in one of these situations. It could be that we notate this situation with S11, situation 1-1, meaning that the pair are in the same cluster under both C and C prime. S00 means the pair are not under the same cluster under both C and C prime. S10 means the pair are on the same cluster in C, but are not under the same cluster in C prime. And S01 is the opposite. It means that the pair is not under the same cluster in C, but they are under the same cluster in C prime. Let's look at a few examples here for this to make sense. So let's find some pairs that fall under S11, the situation that the pair are under the same cluster on both clusterings. So for example, here we can see the pair 1 and 5 are both under the same cluster. They are under the C1 cluster here, and they are under C prime 1 cluster here. Another example is the pair 15 and 18. They are under the same cluster here, or also the same cluster here. Another example is the pair 11 and 8. They are both under the same cluster. They are under the cluster C prime 2 here, and they are under the cluster green here. There are more examples of S11. Actually, try to find a few of them before continuing to watch. Let me find another one here together. So another one could be the 16 and 12. Right? So 16 and 12 are under the same cluster here, but they are also on the same cluster. There are way more than just these 4 examples. You can actually find more. But let's move on to another situation. How about S00? This situation is the one that the pair are not under the same cluster under C1 and under C prime. Under C and under C prime. So let's look at a few examples. So here 5 and 7, they are under different clusters under both clusterings. Another example, 13 and 16, we can see they're under different clusterings on both. And we've got 4 and 17, again under different clustering on both. Let me offer another example here. Let's look at 20 and 1. You can see they're not under the same cluster here. Actually 20 and 2. So I made a mistake. And they're not under the same cluster here either, right? So let's move on to another situation. S10, meaning that the pair is under the same cluster in C, but they're not in the same cluster in C prime. So let's look at a few examples. We've got 1 and 2. We can see that they are under the same cluster in C1, but they're not under the same cluster in C prime 1, in C prime. Another example, 5 and 6. Again, they are under the same cluster in C1 and in C, but they're not under the same cluster under C prime. Another example, 19 and 16. They are under the same cluster here, but they're not under the same cluster here. I'll try to find another example. Alright, here another example. Oh, actually 5 and 6, we've already seen this. Okay, here's another example. We've got 20 and 12. 20 and 12, and also we've got 20 and 12. Right? So another example. Okay, so the last situation is the opposite of S01. S10 is S01. So in this one, we want the pair to be not under the same cluster under C, but under the same cluster in C prime. So a few examples are 4 and 8. You can see they're on the same cluster here, but not here. 5 and 10 on the same cluster here, but not here. And 18 and 19, same cluster here and not here. So try to find a few more examples here. All right, so we've got 14 and 1. They are under the same cluster in C prime, but not on the same cluster in C. Alright, so how are we going to use these situations? So what we do for each of these pairs, we study their states and basically calculate these 4 numbers. N11 is the number of pairs that have situation S11. So on and so forth, we're going to have 4 numbers, N11, N00, N10, and N01. And using these n's, which basically tell us the number of pairs under each of these situations, we come with, there are some metrics that uses these n's. But before we get to those metrics, let us have some understanding of how many pairs we are going to expect to have for a data object that has n, for a data set that has n data objects. So if we've got n data objects, we are going to have this selection of 2 out of n possible pairs. And basically, you're going to expect to have n multiplied by n minus 1 divided by 2 a number of pairs in your data set. And because of that, you expect the summation of these 4 numbers, n11, n00, and n10, and n01, to always be equal to this value. So the first metric that can be used that uses these n's is the range measure. Basically, range measure says that if you've got situations n11 and n00 a lot, that means you've got a lot of similarity between your clusterings. In practice, rands tends to have very high values, even when you compare random clusterings, meaning that you just randomly assign data objects to a few clusters, and again you randomly assign data objects to another clusters. And then you compare them, and still you're going to have a rather large rand in around 0.7. The reason for that is the culprit of that is n00. Even if you don't have a lot of not matched, which most of the time your data objects are not going to be matched, then this is going to have a high value. That's why rand is actually not a really reliable metrics to compare clustering, but this is one of the metrics that is in the literature. But this is good because we are sort of also learning about these metrics, and we can sort of like see the disadvantage of rand, which is going to be the strengths of the other ones. Another one is the Wallace's measure, which we've got W1 and W2, and basically these two only pay attention to N11, and they also calculate based on only the numbers of members in cluster C and once on numbers of members in cluster C prime. And the Folks-Mallows, the one that I most frequently use, is basically a combination of Wallace 1 and Wallace 2. Basically, it is, the multiplication of the Wallace 1 and Wallace 2, and then you get the square root of that multiplication, and then you've got your Folks-Mallow. The Folks-Mallow ranges between 0 and 0.5, and if you've got 0.5, it means you've got perfect match. It's relative, but it's the closer to 0.5, the higher the similarity. And if pay attention, another metric is Jacquard's, which only uses N11 in the numerator and N11 in 01 and N10 in the denominator. Basically saying the N00 is not a significant number when you will want to compare the clusterings. And the higher the Jacquard's index, the better, the more the similarity. So next we are going to move to the second types of metrics that we talked about. Like we said, it's going to be based on set cardinality, and we can see and understand cardinality in a confusion matrix the best possible way. So let's look at the confusion matrix. I believe if you've watched my video, we've talked about confusion matrix, but let's do it one more time here. Basically, when you want to see the relationship between categorical attributes, two categorical attributes, you basically count the number of data objects that have the pair of the possibilities for these two categorical attributes. And let's face it, each clustering basically is a categorical attribute, right? It's a nominal categorical attribute. And because of that, we can use confusion matrix to see the relationship between these two clusters, right? So a confusion matrix for this situation is going to be, the rows are going to be the clusters of one clustering, and the columns are going to be clusters of another clustering. So for example, here we've got two data objects that are under C'1 and they're under C1. So let's find those two data objects. So two data objects are, I believe, are these two, right? So these are those two data objects, right? So let me actually go through this completely. So let me change my color here. And then we've got four data objects under C'2 and C1. So these are those four data objects. And then we've got 6 totally on that front, and then we've got 6 that are under C'1 and under C2. So C2 is there and C'1. So these are those 6. So these are those 6, and that is 0. So we've got 6 here as well. And under C3, so let me change the color here. We've got C'1, 2, and under C3, which is these two, right? So these are those two. And finally, we've got another 6, which are these guys. I need to complete these colorings, sorry. Alright, so now we completed this. Let's complete the table. So we've got 8 here, we've got 10 and 10, which total gives us a number of data objects under each of these clustering. So now that we have this, now we understand what we mean by set cardinality. Basically how many data objects are in the clusters, in the same cluster that are the majority of these data objects are in the other cluster. And using this confusion matrix, we have a criteria, we have a metric that uses this confusion matrix to come up with a number, capture a number, capture similarity using this metric, and that is called H criterion. And basically the way it works, it assigns a best match. Basically say, okay, C prime, what is the best match, C prime 1, what is the best match to C prime 1 from C1, C2 to C3 for each of the clusters in the clustering that has lower number of clusters, and then calculate the numbers of data objects that were not matched, right? So for let's see this example, right? So what's the best match for C prime 1? So what's the best match for C prime 1? Of course is this one, 6, and then what's the best match to C prime 2 is this one. So we calculate the unmatched probability, which are these guys. These are the unmatched probabilities. So these guys are the unmatched probabilities, and we've got 0.4 as the unmatched probability, which tells us that on 0.4 is the sort of the similarity between these two data objects, between these two clusters. Alright, so in this video we learned about what we mean by comparing clusterings, and we learned about two types of ways that we can have metrics that capture similarity and dissimilarity between clusterings. We learned about counting pairs, which basically find the situation, different situation based on pairs in the data object. And then we also learned about set matching, which uses sort of like see the clusterings as categorical attribute, specifically nominal, and use a confusion matrix to see the relationship with them. And the H criterion has a specific and systematic way to come to a number about the dissimilarity between the data objects. Alright, until the next video.